Hello, everyone. It's currently 2 p.m. Eastern Standard Time, and we'd like to get started. So thank you for joining us today. We really appreciate it. My name is Kathy Yankee, and I will be serving as your moderator for the next hour. The topic for our presentation today is GridEdge's Networks is presenting how to safely interconnect renewable generation. And we're going to start our presentation today with the CEO, Nakam Sadan, from GridEdge Networks, and that'll be about 30 minutes, and then we're going to a question and answer session with a panel of experts. And just to give you an idea, we've got a couple of our customers. One representing the utility from National Grid is Fran, and from the IPP, we have Jeremy Lauer, in addition to an industry expert, Bruce Renz. So we got a great panel today, and hopefully we'll have great questions and answers for you. Just a couple housekeeping things before I turn this over to Nakam, but you will note that you can resize your slide box to a size that's convenient for you by just stretching the corners. And on the left side of your screen, you'll see a Q&A box. And feel free to submit the questions at any time during the presentation. We'll take all the questions and we'll do the best that we can to aim to answer everything possible. And if we aren't able to in the limited time that we have, we will get back to you directly with the answers to your questions. So we don't want to leave anything unanswered, and we'll schedule a call or whatever is necessary. Now, without further delay, I'd like to turn this over to Nakam so he can begin the presentation. Nakam?
Thanks, Kathy. Hello, everyone. Welcome to the GridEdge webinar. We appreciate you being here today with us, and the topic of today's presentation is how to safely interconnect renewable generation to the grid. I will start with an agenda for today's presentation. We'll start with a brief overview of the company and the definition of the IEEE interconnection standard requirement for unintentional islanding, followed by the available methods used to comply with this requirement. The description of the DGP technology is at the center of my presentation, including comparisons with traditional DTT and legacy PLC. I will then introduce the DGP system components and follow up with photos from field installations, ending with a high penetration use case. Following the presentation, there will be time for Q&A with our panel of experts, as you heard from Kathy.
There's usually a slight delay. Yeah, it's a delay.
So about GridEdge Networks. The company has been in business for 18 years, was founded in 2001 as Amperion, and renamed in 2013 to better reflect the focus on integration of renewables at the edge of the grid. We have deep knowledge and experience with power line communications technologies and are located in Westford, Mass. Our main product is a complete turnkey solution for anti-islanding applications. It was conceptualized and jointly developed and tested with the largest utility in New England. The main objective of this system is to reduce interconnection cost and interconnection time in order to enable integration of large-scale renewables and high penetration. The system has been available since March 2014, and we currently have 60 field installations with various utility and IPP customers in multiple locations, primarily in the Northeast. 2 of them are participating on our webinar today. The system is based on a platform that uses the most advanced power line communication technologies and provides a secure and reliable foundation not only for anti-islanding but also for future applications. The IEEE 1547 is the interconnection standard for all DER. DER stands for Distributed Energy Resources, and DG is Distributed Generation. I will use the 2 terms interchangeably throughout my presentation. The excerpt that you see here was lifted from the 2018 revision that was published last year. Specifically, Section 8.1 defines the requirements for unintentional islanding. Namely, DER shall detect the island, cease to energize the area EPS, and trip within 2 seconds of the formation of the island. So the standard has 3 requirements. 1, detect the island. 2, cease to energize. And 3, do 1 and 2 in less than 2 seconds. This requirement applies to all DER sizes, including residential and CNI. Our focus is only on grid-attached, large scale, typically greater than 500 kW generation capacity. So why is there a concern about unintentional islanding? Islanding creates a safety risk to utility workers and can also cause equipment damage if not handled properly. Why 2 seconds and not longer? A new study presented last month at the Georgia Tech Protective Relay Conference by Dominion and Virginia Tech University shows an increased arc flash risk to utility linemen with run-on times that are greater than 2 seconds. Their study was focused on the type of PPE gear used by line crews and the assessment of the safety risk. The standard PPE gear will sustain an arc flash if run-on time is less than 2 seconds. With run-on times of 5 seconds, the study showed that the risk increased by close to 70%, and higher rated PPE, which are not standard equipment, is required in that case. It is important to note that sometimes the fault can be created by a utility person working on the line at that very moment, rather than responding to an event that happened earlier. So time is of an essence. The same study showed an increased risk with a larger size DERs in also high penetration cases. So what do we do? How do we mitigate this risk? There are 3 methods to address the islanding problem. The first method, and the most common one, is the autonomous anti-islanding algorithm that comes with every DER. The DER is usually type tested and conforms to the UL 1741 test standard. It does not require any communications and is not controlled by the utility. It is probably sufficient for a single case deployment, but may not be suitable for other cases. A 2018 report by Sandia Labs that simulated mixed DER types of inverters from different manufacturers and inverters mixed with synchronous machines showed that the detection algorithm accuracy is reduced in those cases, resulting in longer run-on times that exceed the 2-second limit. So the AAI method is as good as the proprietary algorithm implemented by the DER vendor. The second method is direct transfer trip, or TTT. It is communication-based and utility-controlled. It is typically preferred by utilities, however, can carry a high cost, especially with direct fiber, and may not be as reliable as is the case with some analog phone lines and some radio links that are subjected to interference. So DTT method is as good as its communication channel. The third method is the main subject of this presentation. That's DGP, Distributed Generation Permissive. It uses a power line conducted permissive signal that is independent of the AAI algorithm and independent of DTT's communications. Since it uses the same lines that deliver power, it is a fail-safe, reliable way of detecting an island condition. One misperception is classifying DGP as a form of DTT. Actually, DGP is a third new way that has characteristics of both AAI and DTT. Going back to the standards definition of 1, detecting the island, and 2, ceasing to energize, DGP behaves like AAI, detecting the island and tripping at the PCC location, while DTT makes both detection and tripping decisions at the substation by a centralized controller that sends a trip command. There is no transfer trip with DGP. The loss of the permissive signal is the indication of an island and that causes a trip. Like DTT, DGP is utility controlled, and a trip can be forced by the utility simply by stopping the permissive signal at the substation. How does the DGP concept work? A permissive signal is continuously sent over the power lines by a DGP transmitter from the substation on the left to the DGP receiver located at the PCC location of the DER site on the right. As long as the signal is present at the PCC location, the receiver does not trip. When there is a discontinuity in the circuit, such as in an island case, the signal will be lost and the receiver will immediately trip. As you can see here on this slide. Here, a midline recloser opened and the signal is stopped due to the gap created in the path. The result of the signal loss is an immediate trip by the receiver of a disconnecting device, such as a PCC recloser or a breaker. So going now from a concept to a field implementation. These are photos that were taken in 2013 of our first field installation. The signal runs from the substation on the upper left to the solar site on the upper right and going through medium voltage distribution poles that include 2 midline reclosers. Using the same circuit with the 2 midline reclosers, I'd like to show you a side-by-side comparison of DTT with DGP. DTT equipment and its communications lines are represented by the blue lines, while DGP equipment using the power lines are in red. The DTT method requires installing a device at each midline recloser to send its state back to the substation. A centralized controller at the substation then decides to send a trip command to a DTT device at the PCC location. In this case, 3 communication lines are required. DGP does not require installing equipment and midline reclosers and does not require communications. Lately, there's a growing trend of pushing everything to the cloud, and some are researching the use of cellular technology for DTT. For this particular circuit, a cellular modem will be installed at each of the 4 locations, associating with the nearest cellular tower that is represented here by an orange triangle. A virtual private network tunnel is used to provide security over the public cellular network. While the security aspect is being addressed, the biggest concern with this technology is availability and response time. Actually, GridEdge is a user of this technology. We have virtual private networks with both Verizon Wireless and AT&T that are used daily for data monitoring of the 60 systems we have in the field. Our user experience shows that while cellular can be used for metering and monitoring applications, it is not suitable for mission-critical applications such as protection and control. We encounter daily problems with devices not connecting or with slow connections that take minutes to download a file. Both carriers are racing to replace 3G with 4G technology and then 5G while moving bandwidth around and causing stability issues. The private tunnels address security concerns, but do not address the need to be 100% available and responsive. The next set of slides describes the DGP system. The DGP product has 3 components: a DGP modem that contains the electronics, which is the brain of the product, a pair of couplers that are passive devices enabling safe injection and ejection of the permissive signal on the power lines, and a pair of coax cables connecting the modem to the couplers. A basic DGP network will always contain 1 transmitter and 1 or more receivers. On some circuits, additional units called regenerators are required to be installed in between the transmitter and receiver in order to boost the signal and extend its reach. A regenerator is actually a combination of an upstream receiver and a downstream transmitter. Connection to utility and customer interfaces is done with contact closures. Every unit has a built-in data monitoring function that runs continuously and collects signal performance and health information in real time. The data is stored locally and can be used for analytics and troubleshooting. Here you see a pole construction drawing showing the 3 components that make up the DGP system: the couplers, cables, and the modem cabinet. In addition to the GridEdge supplied equipment, the utility will need to provide a bracket or crossarm for mounting of the couplers, cutout fuses, and lightning arresters. It's important to note that the arresters are there to protect the couplers, not to protect the line. The pole-mounted equipment installs on energized lines without taking an outage and without causing a service disruption. It usually takes a line crew less than 4 hours to install a DGP pole. The two end units can interface to utility and customer equipment using dry contacts. The dashed line on this slide represents the boundary between the DGP network and the other equipment. The utility can force a trip by closing a dry contact at the transmitter on the left, represented by the blue arrow. The receiver on the right trips the PCC recloser using an output dry contact represented by the red arrow, and senses the state of the recloser using a dry contact input. Being a private network that is isolated from the public internet, the DGP system is highly secured. This is a sample installation with two regenerators. Couplers are installed on phases 1 and 2, represented by the blue and red lines on top, and the signal is generated by the transmitter located at the substation on the left and traveling towards the receiver at the DG site on the right. Unlike amplifiers or repeaters that echo the same signal, regenerators are different. They terminate the upstream connection and start a new downstream connection. In order to do this, DGP uses a combination of frequency and time domain multiplexing. This is represented by the 3 links. The first link, shown as a green bent arrow, uses frequency 1 in time slot 1. The second link, shown as a blue bent arrow, uses frequency 2 in time slot 2. And the third link, shown here as a purple bent arrow, uses frequency 3 in time slot 3. Another misconception is categorizing DGP as power line carrier. While both technologies use the power lines for sending a signal and utilize the same frequency spectrum of 50 to 500 kilohertz that was allocated by the FCC for utility use, everything else is different. The output power of the DGP modem is 0.1 watt, which is orders of magnitude lower than the 10 watt or higher that analog PLC puts out. The DGP technology was designed 7 years ago using 21st century digital signal processing technology versus the 1970s old analog PLC. The use of frequency and time domain multiplexing enables regeneration to extend signal reach over distribution lines. PLC simply cannot do that. With DGP's frequency separation, there's also no need for wave traps that legacy PLC uses as frequency blockers. DGP uses phase-to-phase coupling that enables operation on 3-wire ungrounded systems and provide increased reliability. The 2 phases are matched in length, providing a reliable return path for the signal and avoiding the use of the ground as a return path. PLC uses a single phase-to-ground coupling on high-voltage transmission lines. It cannot be deployed on distribution lines that service customers and are not express feeders. And lastly, GridEdge invented the differential coupling technology to increase signal-to-noise ratio. This diagram below was lifted from one of our patents. These are photos of typical field deployment with a permissive signal traveling over the power lines from the substation on the left to the PCC location on the right. More photos of field deployments are shown on this slide. The solar panels can be seen in the background of the lower left photo. Solar panels, I know it's probably hard to see, it's really way in the back, but they are in the background of the lower left photo. This is a typical configuration of a PCC location with 4 poles. A riser pole connecting to the solar equipment using an underground power cable. In front of it, in front of the riser, there's a CT-PT pole with a utility meter in front of it. And in front of the metering package there's a PCC recloser pole, which is the PCC recloser that DGP trips. Not seen in this picture, in this photo, is the DGP pole in front of the recloser. The receiver cabinet is seen in the center bottom photo with a pair of couplers above it. The top right photo is a substation installation with a transmitter cabinet and couplers installed on the steel structure. Looking inside the receiver cabinet in the middle photo here, there's a DGP modem at the top with the data recording device to its left, and the two coax cables coming in from the bottom of the cabinet into a combiner circuit in the modem box. The knife switches with the dry contacts can be seen below the modem. The bottom right photo is a close-up of a 24 kV coupler, and above it is a cross-arm with a pair of mounted couplers. I hope that this gives you a feel for the installed equipment in the field. So the next two slides illustrate the economic benefit of the DGP solution to an IPP customer. This is a real case in 2014 when an IPP approached GridEdge with a request for a quote on a new greenfield solar project. They were instructed by the utility that DTT is required for their project, and they should approach the phone company directly. When they did, the carrier told them to get in line and wait 6 months for the phone line installation since their queue was already full. The IPP was under pressure to start making loan payments as soon as possible and could not wait that long, so they approached us. GridEdge committed to delivering 6 weeks and completed the project ahead of schedule. The ability to reduce the interconnection time and generate revenue sooner was very significant in this case. The second case is a retrofit project. The IPP customer already had a phone DTT system installed, but suffered long outages and loss of production revenue as a result of nuisance tripping caused by unreliable phone lines and faulty equipment. Learning about GridEdge as a viable alternative, the customer installed the DGP system in 2015 and had return on investment in less than a year. This is a calculation of the savings over an accumulated period of 20 years, being the typical life cycle of a PPA. On top of the revenue loss caused by poor reliability, there's also monthly fees that are paid to the phone company for the use of the leased lines. And to make things worse, in some areas, the carriers are discontinuing the leased line services, and utilities are faced with an urgent need to find an alternative. The next set of slides describe a high penetration use case installed in 2018 with 10 solar sites on a 23 kV distribution circuit. A single transmitter is installed inside the substation, which is represented here by the blue box on the right. The green boxes are receivers installed at 8 PCC locations. The yellow panels represent the solar sites. You can see that the first PCC location, PCC1, has 3 sites behind a single PCC recloser. The main circuit is 13 miles long from the substation on the right to the end of the feeder on the left. The side streets above and below the main road are 2 to 3 miles long. This circuit services residential and industrial customers and has 7 reclosers and sectionalizers. 8 regenerators were required to boost the signal to reach all 8 PCC locations. This deployment was featured in an article published by Eversource in TND World magazine last November. I highly recommend all of you to read the article as it contains more details about this project. This graph clearly demonstrates the cost effectiveness and scalability of the DGP solution. It shows the number of devices required for each interconnection in each interconnecting IPP. The first customer at PCC1 needed 4 devices. At transmitter, 2 regenerators, and a receiver. The second and third customers at PCC2 and PCC3 required only 2 regenerators and their own receiver. Customers 4 and 5 only needed to pay for 2 devices, a regenerator and a receiver. And customers 6, 7, and 8 only paid for their own receiver. So in addition to the reduced cost, this one-to-many architecture also reduced the interconnection time for the new DG customers. This high penetration case validates the concept of what we call a DG-ready circuit. By having a permissive signal already present on the line, it becomes very simple, fast, and cost-effective to add DG sites either at the end of the feeder or in the middle. Unlike DTT, there's no need to go back to the substation and add equipment or reconfigure the protection scheme. While commissioning this project, we also noticed 2 cases of self-tripping by the AAI algorithms of solar inverters that were only a quarter of a mile apart. The self-tripping stopped after the settings were changed following the installation of DGP as the primary anti-islanding protection method. So in summary, DGP can be used as a primary or as a backup to AAI protection. As a fail-safe system, it is 100% dependable. This statement is backed by real data collected from our systems over the last 5 years. There was no single case when an island was formed and DGP did not trip. Never. The data monitoring capability proved to be extremely useful, not only for performance measurements, but also to reduce downtime of the DG plant by providing an early alert that a trip event has occurred. Since we monitor the sites daily, GridEdge is usually the first one to notice a disconnected DER and notifies the utility and the IPP customer. An immediate action can then be taken to investigate the cause and address the island. This service is very valuable to the IPP since the cost of just 1 day of outage can more than cover the annual service fee for the data monitoring. Looking to the future, the DGP platform will be expanded to support new functions as required by the new 1547-2018 standard. While at present, the DGP solution for anti-islanding represents a new option that I would like all of you to consider for your DG project. Thank you for your attention.
Thank you, Nachum. That was great. And I apologize for a little bit of the animation in the middle. It looks like the slides had a life of its own. So I apologize for that. We're going to now switch over to the Q&A portion. And before we begin, I'd like to introduce our panel of experts. First, we have Fran Kane. Fran is the National Grid Energy Integration Consultant in the Customer Energy Integration Department at National Grid. The Customer Energy Integration Department at National Grid provides the customer interface for interconnecting distributed energy resources from application through the life of the project. And so Fran will be giving you an idea how it is from a utility perspective to be a customer of GridEdge Networks. From the IPP perspective, today we have Jeremy Lowry from Ingenco, and he's the VP of Electrical Controls Engineering. He manages all the electrical controls and SCADA-related projects and equipment at Ingenco. And finally, from an industry visionary, utility visionary, we have Bruce Renz. Bruce has been working with GridEdge since its inception. He is the president of Renz Consulting, and he formerly was the vice president of T&D services at American Electric, and is very involved in the DOE on Modern Grid Initiative. So we've got some great panel here, and we're going to start off with our first question. So please don't hesitate to submit some questions. We already have one. We're going to start out with just a simple one and ask both Jeremy and National Grid, why they chose the GridEdge solution. So with that, I'm gonna let Jeremy go first. Jeremy, the floor is yours.
Oh, okay, thanks. Yeah, we looked at lots of different solutions because the system, the transfer trip system that we have was a GTT with the phone lines, analog phone lines, and we just have a lot of problems with them. They're all managed by Verizon, and Verizon is kind of not really concentrating on this type of technology anymore, these type circuits. They're more focused on wireless and fiber, so they have very few people that can service the circuits when they do go down. So pretty much, I would say half of the thunderstorms that would roll over the plant would take out the circuit, and sometimes it was days, and several times it'd be weeks before the Verizon circuit would get back online. So we were looking very heavily trying to find a different solution to this, and GridEdge was the only solution that the utility would allow us to try. So that's why we moved forward with the GridEdge on a pilot plant, and it worked at the pilot plant, and then we ended up installing it at 2 more of our plants.
Okay. Great. Thank you, Jeremy. I'm now going to open the line for Fran.
Thanks, Kathy. I think a similar issue with National Grid, although it was a little bit more driven by the customers and developers that were developing DER sites. They were not satisfied or happy with the DTT costs estimates that National Grid was providing, and also, as Jeremy said, the dependency on Verizon. And at least in upstate New York, Verizon circuits take quite a bit of time to get. So there was some pressure from the Public Service Commission in New York to find a different solution. And so we were looking for the alternatives, and one of the things that was available was GridEdge to not only from a cost standpoint, but also a schedule standpoint to get the projects implemented sooner. So it was decided with two of our feeders. There were some projects that lent themselves to this, and we decided to do a pilot project with GridEdge and see how it would work. And we're actually just in the process of finishing up that process.
Okay, thank you, Fran. We're going to switch to another question. I have a site that operates 12.47 kV, and the distance from the substation to the DG is 17 miles. How many RGs would be required? I'm going to turn that over to Nakam.
Yes, I'll take this question. Thank you, Kathy. So the simple answer depends. It depends on the circuit. If this is an express feeder, no RGs are required. Our longest installed system is about 20 miles long, and the longest single run is 14 miles with margin today. It's actually in Virginia. It's actually one of Jeremy's sites. So if there are no laterals or taps on that circuit, if this is an express feeder, no RGs will be required for your 17 miles. If this 12.47 kV circuit, which I assume is a distribution circuit that services customers, has other equipment on it, we will need to do a site survey and come up with a system design, and that will determine how many RGs will be required. So there's no one-size-fits-all, and it's not simple to answer this question. Every circuit is different. We model the circuit using a process that we developed here in-house, and when we model the circuit, we look at it from a high-frequency perspective, not at the 60 hertz perspective. And after modeling the circuit, we come up with a system design that determines how many regenerators are required and also their exact pole locations on your circuit. And that's part of the engineering services that we provide.
Okay, we'll go to the next question. This is similar. Do you want to?
Okay, I'm going to read the question. What is the length of the longest feeder of which you have deployed this equipment? So yes, I kind of answered in passing that our longest deployment is 20 miles long with regenerators. However, as point to point without regeneration, it's 14 miles, and there's still margin. So I believe that we can do, on an express feeder, we can go 20 miles without regeneration.
Okay, we have a question about what is the reliability history of the DGP equipment? And I'm thinking maybe Jeremy and Fran, you might want to answer from your perspective. Yep.
Let Bruce.
Bruce, you haven't spoken. So we'll start with Bruce. Bruce?
Yeah, thank you, Kathy. The reliability can usually be broken down into two categories, security and dependability. From a dependability perspective, which could be defined as it always operates when it has to, the system has been 100%. And from a security point of view, the concern is always for nuisance trips, where the system trips when it's not supposed to. These occur infrequently, but they're not zero occurrences. And generally speaking, it's considered quite acceptable.
Okay, thanks, Bruce. I'm going to turn it over to Jeremy and just talk about your experience and the reliability.
Yeah, so if we kind of break the equipment into different pieces, the radio portion has been extremely reliable. I don't think we've lost any radios or had any issues with any radios, maybe one, but I'm not even sure about that. And the only issues we've really had are some of the radios, some of the surge protection has gone, has faulted out, but that very well may have been just because there was a lightning strike or something near the radio. And then the other piece of the equipment is the couplers, and so we were one of the first to get the equipment installed on a 34.5 kV line, and there were some issues with those couplers, and Knockham went to the drawing board and redesigned some couplers, and so now we have the Gen 2s, and the Gen 2 coupler is so far 100% reliable. In terms of nuisance tripping, two of our sites really have had no nuisance tripping at all that I can think of, so 100% improvement over the Verizon experience. And then one of our other sites is a bit more challenging. It has a lot more regenerators, more noise in the area, and we're still tweaking on that one and improving it, and we're getting closer to 100% reliability on our third site.
Great. Thanks, Jeremy. Now I'm going to switch it over to Fran for his perspective from being a utility. Fran?
From our perspective, as I said, we have a total of 4 projects connected on 2 different feeders, Both feeders have been performing well. The one feeder has a single project, and once that was commissioned and tested, I don't believe we have had really any issues on that one. The others, the projects were added in sequence, and as they were added, there was some work that had to be done to stabilize things. But now that that's been done, I believe we've been working very well and haven't had any real issues since earlier this year, once the system was completed. So we've had very good luck at this point.
Okay, thanks, Fran. And Nachum?
Yeah, thanks, Fran. I just wanted to chime in on your experience with the system. So this is a subtransmission project that has 4 solar sites currently on it, and they were added incrementally. So first we had 1 solar site. This was 2.5 or 3 years ago, and then 2 more were added last year, and then the last one, number 4, was added at the end of 2018, and we had some challenges there, and it took us 5 on-site visits to actually figure out what was going on. What ended up being the issue was arcing coming out of the solar site, and the arcing was on one of the phases that we have a coupler, and it was affecting our signal transmission. It took some effort to isolate the issue and figured it out that the interference was coming out of the solar site. With the customer, we went in to investigate, and we isolated the problem as one of the phases, phase C, inside the metering cabinet. It turns out that when the construction was finished, it was the dead of winter in December, and the phases were not torqued entirely according to spec. So in this particular phase, it was loose and it was arcing and causing interference to our signal. That's how we found it. But eventually, it would have caused a much bigger problem to the customer. So once this was identified, they replaced the bushing, they tightened it according to the spec, and then the problem went away. So just I'm telling you this just as an example of how complicated this work can be as a system integrator. You have to deal with variables, other elements in the field that are not under your control. However, we need to understand what is happening, not just to our equipment, but also to the customer's equipment. And in that case, it took, as I said, 5 trips on site and a couple months to figure this out. And once it was identified and addressed by the customer, all the problems went away. And as Fran said, the system has been 100% reliable since then.
Okay, thanks. We're going to switch over to another question. What are the extended functions as related to IEEE 1547-2018 that you were referring to? So I think that's for you, Nachum.
Well, I will actually delegate it to Bruce.
Okay. All right.
Since we work together on putting the roadmap for this
Great.
For the new standard.
Bruce, it's back to you.
Bruce?
Bruce, you might need to unmute.
How's that?
Much
That's
better.
good. So the question was, what are the extended functions as related to the new IEEE standard?
Right. The new IEEE standard recognizes that distributed resources can produce more than just baseload energy, particularly as renewable generation is combined with storage. DER operators with smart inverters can now offer a variety of ancillary services, such as volt bar control, spinning reserve, smoothing of renewable variability, and many others. The new standard also recognizes that the optimal application of DER requires much more intelligent grid with extensive communications and computing capability. As a result, communication requirements for all distributed resources have been added to the standard. GridEdge can provide a platform to support these growing requirements. The DGP system already communicates with distributed resources that require advanced anti-islanding. The same platform can be enhanced to become the front end of distributed energy management systems, otherwise known as DERMS. Combinations of PLC and cellular are now included on GridEdge's product roadmap, a roadmap which visualizes 3 levels computing and communication architecture that links DER, substations, and regional control levels. Whether applied by utilities or aggregators or some new entity, the system will help fill a need of this industry.
Thanks, Bruce.
All right.
Next question.
All right, let me go to the next question.
Yeah, so the next question was about a capacitor bank and a voltage regulator. How do we deal with that? And I mentioned earlier that we do a site survey. As part of the site survey, we model everything that's on the 3 phases, everything that's installed on the poles, including capacitor banks and voltage regulators. So they go into the link budget calculation in our modeling software, and then we come up with a system design that addresses that. We actually have many systems that have, almost every system, a distribution circuit has capacitor banks on it. So we know how to deal with that. And some circuits also have voltage regulators on them. So they are already deployed in the field, and as I said, they will be part of the system design.
Okay, let's talk about scalability, and maybe we can talk about as you grow new sites, how does that affect the reliability, the scalability of the system? And I don't know if Fran, you might want to speak to that?
That will
No?
be either me or Bruce.
Bruce? Okay, Bruce?
Yeah. Obviously, as you expand the system, you need to look at the signal propagation issues. And as Naka mentioned, anytime a new site is to be added to the line, a site survey is done. Signal transfer functions are measured between the sending and receiving location. Signal-to-noise ratios are established. And then a proper level of signaling needs to be produced. Once that's done, a period of testing, anywhere from days to weeks, is put in place in order to establish the performance of the system. And only when it passes that kind of acceptance testing is the system commissioned. Following a procedure like that, as both Jeremy and Fran have mentioned, the system becomes quite stable. As said before, it performs 100% dependably and with very little in the way of nuisance tripping.
Okay. And we'll kind of extend off this with another question.
I just wanted to chime in on what Bruce just said. You know, for this reason, we developed the monitoring software, and that has analytics and it has the daily reporting capabilities. So we want to back this up with data, and the data that we collect in every unit continuously is going to be used in order to address any exceptions, if there are any, and provide performance reports that would help us extend the system and scale it.
Okay. All right. If a DG deploys and pays for the DGP system, why would a second DG be allowed to piggyback onto the original system? Does the second DG affect the reliability of the first DG even temporarily?
So I will take that. So as you saw in the high penetration use case that I talked about, the last 3-4 customers only needed to add a receiver. A receiver is a passive unit. A receiver just receives the signal. So adding a second DG to a first one does not affect the performance of the first DG, the first site. Now, of course, when we commission the systems, just to be on the safe side, we lift the knife switches. I mentioned that the knife switches electrically isolate the units from the customer interface. So when we commission, in this example, this question, the second DG, we will lift the knife switches of the first DG so that if anything happens inadvertently, we will not trip the first site. But the second site should not affect the first one. Now, the first question was, why should the second DG benefit from the fact that the first one already paid? Well, that's a benefit for the second. In this case, I guess it pays not to be first. But the benefit of a DG-ready circuit, this whole concept, is to benefit the second, third, fourth, and so on DGs that come online, enabling large-scale integration of renewables. That's the whole idea.
Okay, great. I'm going to turn this next question over to Jeremy. How long does a typical system take to design and deploy? So I thought maybe from a customer perspective, you could talk about it, and then we can add if there's a need for it.
Yeah, well, the simple answer is it's a lot faster than a system with Verizon. So you're going to benefit hugely and going with the GridEdge over something with Verizon, and it's going to be more reliable. I don't necessarily remember how long it took, but it was, I don't know, from start to finish, maybe a couple months for the first site. From the moment we decided to go with GridEdge to the equipment showed up to the installation and then and commissioning the system, maybe a couple months, might have been quicker than that. So it also depends on, you know, how far away and what is in between the DG and the substation. So the more stuff, the more generators, the longer it takes. But we're talking, you know, 1, 2, 3 months as opposed to some Verizon circuits taking 6 months to get installed.
Thanks, Jeremy. Maybe Fran can comment as well.
Yes, and now I'm going to move it to Fran for your perspective from a utility standpoint.
From our standpoint, I don't think the time frame was impacted as Jeremy said. It was not the critical path, and the installation was in parallel with the construction of the sites, and so you know the utility side at the substation in our case you know was completed you know prior to the developer, the customer, being ready at their site. So it's really follows the same timeline as the site construction, and really the availability of the equipment, which I think Malcolm would not be a critical issue based on typical construction times. So
Okay.
I think 9 months to 12 is our typical timeline with the developers, and that would easily be met.
Yeah, it's more that what you're saying, Fran, is it's more your utility time frame, you're not impeded by GridEdge.
No, not at all.
Okay. Malcolm, did you want to add anything?
Yes, thank you both, Fran and Jeremy. So, usually we are not the entity that holds the project, rather the contrary. And we are actually currently offering a pilot program for anyone who is considering switching from an existing DTT system that is causing them grief, such as a phone DTT, and offering to put a GridEdge to the test side by side with the phone DTT and run it for an acceptance period, and then switch over if we meet the acceptance criteria. So in doing it that way, actually there's no time delay since this switchover will be quite immediate.
And no issue of downtime either.
Yes, since they're already protected with an existing DTT system.
Yeah. Okay, we're going to go to another question. We're almost wrapping up here, so we're probably not going to get to all the questions, but we'll keep moving. If a regenerator fails, will the DG trip? I'm going to give that one to Malcolm.
Yes, I'll take this one. So yes, if a regenerator fails, it will not pass on the signal. So therefore, the signal will not be seen by the receiver, and the receiver will trip.
Okay, let's see.
I think we have time for one more question.
Yeah, one more. Let's see.
Okay.
The question is, does GridEdge have to monitor the DG equipment? I'm concerned about cybersecurity issues.
Okay, that's a good question. So first of all, let me answer the concern. You shouldn't be concerned about cybersecurity, since even if, let's say, our Verizon Wireless and AT&T virtual private networks are being affected, are being breached somehow, all they can do is just look at the monitoring data. The monitoring data is not affecting your protection system. The modem device inside the cabinet is responsible for the protection signal, and it does not have any inputs. It only has one output. That's the serial port that connects to the monitoring device. So even if somehow someone gets into the monitoring device, they cannot do any harm to your protection system. So first of all, you're fully protected. Now, secondly, the first question was, why does GridEdge need to monitor? No, we do not need to monitor. We are just offering it as a service. We think it would be useful to offload your SCADA group or other group that does monitoring in your organization from doing that every night. We offer that as a service. We monitor all of our 60 sites every night, and we provide alerts and reports every night as a service. So the answer is we don't have to, but we provide it as a service. We think it's a valuable service. If you would like to do it, we can work with you to facilitate that.
Okay. I don't know if Bruce, Jeremy, or Bruce, if you have any last comments before we close up.
The only comment that I would make is that the fact that the performance of the DGP system is very predictable can be very useful in terms of coordination with the other protective systems on the circuit. Certainly, reclosures have a reclosing sequence, and that can be coordinated properly with the DGP system such that the number of false trips or unnecessary trips to the end customer can be minimized. So this is a subject that takes more discussion, but just generally a heads up that the predictability of the timing of the DGP system allows better coordination with all of the existing protective relays on the circuit.
Okay, thank you, Bruce. We're at the top of the hour, and so I'm going to thank our panel of experts and Nachum, and we do have questions that we were unable to answer, but we will get back to everyone who has questions. No worries. We appreciate your time, and we'd love to hear your feedback as we do more of these webinars in the future. So thank you, and have a great day.